Thank you for watching this Labcast. My name is Zhou. The paper I'm presenting today is MELM, Data Augmentation with Masked Entity Language Modeling for Low-Resource NER. In this work, we're focusing on the task of name entity recognition. A quick recap, NER is the task to locate and classify name entity dimensions into predefined categories, such as person names, location names, and organization names. It is often solved in a sequence tagged manner, where each token in the sentence is assigned a separate label, indicating whether it is the beginning token, inside token of an entity, or an outside word. Same as many other NLP tasks, NER also suffer from insufficient annotated data. However, it is difficult to apply simple data augmentation methods such as word replacement or back translation to NER due to the label token misalignment problem. For example, if we replace European Union with Washington has, the augmented sentence no longer align with the original label sequence because Washington is a location entity and has should be tagged as an outside word. Previous works attempt to avoid the token label misalignment issue by either substituting entity with existing entities of the same class or only applying multiplication on context words. However, their performance improvement is still unsatisfactory. In this work, we propose masked entity language modeling, in short, MELM, as a novel data augmentation framework for low-resource NER, which effectively increases entity diversity in training data while tackling the token label misalignment problem. MELM is built upon masked language models, which masks entity tokens and make predictions from context words, and generate a new sentence as augmented data. However, although the predicted words fit into the context, they might not align with the original labels. Therefore, our MELM explicitly injects label information during data augmentation to ensure the generated tokens are compatible with the original label sequence. I'll delve into the details step by step. We start off with the label sequence linearization step, as we would like to explicitly take label information into consideration during masked language modeling. We insert the label token before and after each entity token and treat them as normal context tokens. For the example sentence, European Union agreed to the proposal, where European Union is an organization entity. We insert B.org before and after the token European and I.org before and after the token Union. In order to utilize pre-trained semantic information and accelerate training, we initialize the embeddings of label tokens with those of tokens semantically similar related to the label names. For example, we use the embedding of the word organization to initialize special token B.org. We then fine-tune MELM on the linearized sentences. Specifically, we randomly mask entity tokens in the linearized sentence with masking ratio eta. Then, MELM is trained to maximize the probability of the masked entity tokens and reconstruct the original linearized sequence using a common language modeling loss. After we have obtained the fine-tuned model, we apply MELM to replace entities in the original training samples. To increase the diversity of augmented data, we adopt a dynamic masking rate sampled from a Gaussian distribution. It is noteworthy that as we fine-tune and generate on the same data, the top prediction is likely to result in an identical augmentation. Therefore, we instead randomly select from the top 5 predictions as the substitution. We repeat the above generation procedure multiple rounds to produce multiple augmented examples for each sentence. Next, we remove noisy and less informative samples from the augmented data. By training an NER model with the available gold training samples and use it to tag the augmented sample, only augmented sentences whose predicted labels are consistent with their original labels are kept and merged with the original training set. When extending to multilingual NER, it is straightforward to apply MELM on each language-specific data separately. However, we would like to further integrate MELM with code mixing to enhance the model's multilingual adaptability. A simple code mixing strategy replaces the original entity with entities of the same class from a different language. Although this ensures the label compatibility, the code mixed sentence might not be semantically fluent. Thus, we propose an entity similarity search algorithm to propose high-quality code mixed data. Specifically, we first collect label-wise entity set EIY which contains entities of class Y from language I. Given a source language sentence, we aim to substitute a mentioned entity of label Y with the target language entity E sub from the entity set E, target language Y, such that E sub is most semantically similar to E. In this work, we adopt Mu's bilingual embedding and calculate an entity's representation as the average of Mu's embedding of its component words. Then, we rank the cosine similarity between original entity E and all candidate entities and choose the most semantically similar entity as the substitution. We further generate more augmented data on the co-mix samples. Note that the input sentence now contains entities from different languages. Thus, we also prepend a language marker to the entity token. To elaborate the effectiveness of MELM, we conduct experiments on the 3 scenarios, namely monolingual, zero-shot cross-lingual, and multilingual low-resource NER. We adopt the popular Cornell NER dataset and downsample it to contain 100, 200, 400, and 800 entities as our low-resource datasets. We use XLMR base to initialize MELM parameters and use XLMR large with CRF as our new model. The experimental results on monolingual and cross-lingual NER are shown below. As we can see, the proposed MELM consistently achieved the best average result across different low-resource levels. To assess the efficacy of the proposed language label sequence linearization, we directly fine-tune MELM on mask sentences without linearization, denoted as MELM without linearize. We observe a considerable performance drop compared with MELM, which proves the label information injected via linearization indeed helps MELM differentiate different entity types and generate entities compatible with the original label. For monolingual NER, we experiment with 2 co-mixing strategies: co-mix random, which randomly substitute entities with entities of the same class from a different language, and co-mix ESS, which adopts our proposed entity similarity search algorithm. We observe the performance gains by co-mix ESS is more significant, which demonstrates the effectiveness of our proposed method. Applying MELM on both Go data and co-mix data, the multilingual NER performance is further improved. We further analyze the augmented data to demonstrate the effectiveness of our MELM in maintaining the consistency between the original label and the augmented token. As we can see, between MELM tends to generate generic words such as a, z, he, and she, and the majority of generated words do not belong to the original labels. Being fine-tuned on sentences with entities masked, MELM without linearized learns to predict entity-related words. However, without the explicit guidance from labeled entities, it is still too difficult for MELM without linearized to make valid predictions solely based on the ambiguous context. Compared to the above methods, our MELM takes both label information and context into consideration, and thus generates more entities that fit into the context and align with the original labels as well. Moreover, it is noteworthy that MELM can leverage the knowledge from pre-trained models to generate real-world entities that do not exist in the original training set as well, which essentially increases the entity diversity in training data. As introducing unseen entities can effectively provide more entity regularity knowledge and helps to improve NER performance, we also examine the amount of unique entities introduced by different methods. As the baseline methods suffer from token label misalignment, a large amount of generated entities are filtered out. In contrast, MELM introduces a significantly larger number of unseen entities in the augmented data, which explains its superiority over the baseline methods. To summarize, in this work, we propose MELM as a data augmentation framework for low-resource NER, which boosts entity diversity by generating novel entities, tackles the token label misalignment issue by label sequence linearization, and integrate with code mixing in multilingual NER. Evaluated on monolingual, cross-lingual, and multilingual NER, MELM achieves substantial improvement over the baseline methods. That's all with this lab test. Thank you.